Hello. So, this video, we're aiming to develop a new technique to handle sort of a special collection of types of derivatives, or sort of a special situation. So, namely, we want to develop a technique that's going to be useful for handling derivatives of functions that are products of a whole bunch of factors put together. Okay. So, let's say, for example, we want to take a derivative of this thing. Now, with the tools we really have two options on how we would take the derivative. So the first one is we could just sort of tackle it as is. So we could just sort of jump in. We'd have at least 4 product rules, depending on how you're doing this. You'd have a quotient rule, a bunch of chain rules. There's a lot of rules, a lot of steps, a lot of places where mistakes can get made. The chances of sort of going through all of that work and having a right answer, not great. Not to mention it would take forever, right? Now, the other way you could do it is you could expand all of those things out, right? You could actually multiply out x plus 1 squared and x minus 2 cubed, and then put those two things together and then multiply all of that times x plus 3. Yeah, good luck with that. Like, that's going to be even more steps, more room for error, chances of coming out with something correct, pretty slim. And even then, you're still going to have a quotient rule and at least 1 or 2 chain rules on top of that. So this is sort of a nightmare situation. So you might be looking at this and going, okay, yeah, but you made this for lecture, like, when are we really going to run into this? And that's the bad news. It turns out this kind of function in this kind of form is actually super common. And there's 2 reasons for this. One, polynomials, which is essentially what this thing is on the top and bottom, those are the sort of go-to versions for computers. Computers actually have no idea how to deal with things that really aren't polynomials. They don't know how to deal with exponentials very well. They don't know how to deal with square roots at all, and they have no idea what a log is. But it turns out that if you go far enough in calculus, so if you go into calculus 2 or if you go into survey 2, you'll encounter something, most likely, depending on which class you're going into exactly, called Taylor series. Taylor series are a way of taking any of those functions and turning them into a polynomial, which is exactly what a computer does. So all that to be said, polynomials are ubiquitous. They are everywhere. Even things that aren't polynomials are polynomials to a computer. And the other bad news is that this particular form, having polynomials be factored, is super useful, which we've used all the time, right? This is how we do things like sign charts and find zeros and find domain restrictions. So sort of ideally, whenever you're handed something for an expression that a computer would actually be used on, which is basically all of math these days, its sort of ideal form is exactly this. So thinking that this is sort of a rare occurrence is unfortunately just not true. This kind of thing is everywhere. Now, there is some good news, such as it is, which is that there is a better way to tackle this. We can do this using implicit differentiation. So I know you're probably thinking, like, implicit differentiation, but that's an explicitly defined function. Like, there's not even sort of a hint of implicit. There's no logs that are secretly implicit in the background. I don't think of, x as a function of some hidden variable. It is just x. Like, how is this possibly implicit? But don't worry, we can always make things worse. So instead of just using the function that we have, I'm going to go ahead and introduce natural log on both sides. Now, you may be asking yourself or screaming at the screen right now, why on earth would you possibly want to inject logs into this situation? It was already terrible, and now we're going with a function that you really can't even sort of get a good mental grasp on what it's doing. But there is a method to the madness, maybe more madness at times, but there is a method going on here, which is that the log rules, those rules you learned along with all those logs are going to pull us out of this sort of awful situation. At least that's the hope. So our goal then is to use those log rules, which, as a reminder, we have sort of these three primary ones that we're going to use. So log of a product, log of a times b, is the sum, right? So the log of a plus log of b. If I'm doing division, then log of a over b is log of a minus log of b. And if I have a power, I can take that power and pull it out front. So log of a to the b is just b times log of a. So these are the three sort of rules we're going to use to basically rip apart that big factored form that we had. So it looks intimidating, looks awful, but bear with me. I promise this is going to be worth it in the long run. So we have natural log of y is natural log of this behemoth, right? But we're going to split this apart. So we can think of it as the log of the top minus the log of the bottom. So everything in the bottom is going to get a minus sign. And then all of these things that are getting added together, we break apart with addition. And all the powers become coefficients, right? They all come out front. So this x plus 1 squared is in the top, so it's positive. The square comes out front, so it's 2 times log of x plus 1. Okay. Same with x minus 2 cubed. The 3 comes out front. I get log of x minus 2. Log of x plus 3, there's no power or anything, so it's just there. Stuff in the bottom all becomes negative, so I have minus log of x minus 7, minus log of x plus 5, minus of log of x minus 1. Okay. So, okay, I've applied log rules. Let's maybe just assume that I did it right, hopefully, but it's still not clear why, right? Like, why would I do this? It seems to be getting worse as we go. But remember, we know how to do the derivative of natural log, and it's not that bad, right? So natural log's derivative, right? If I have derivative with respect to x of natural log of some u, then it's 1 over that thing, 1 over u, times whatever the derivative of that thing, right? That's the chain rule. So in particular, if I'm looking at sort of one of these logs, so let's say I'm looking at natural log of x plus 3, then taking the derivative of that would be, right, natural log of x plus 3 is, the x plus 3 is u, so it would be 1 over x plus 3 times the derivative of x plus 3, which is just 1. So the derivative of this term, this natural log of x plus 3, is just 1 over x plus 3, okay? All right, deep breath, almost there. So let's see what we've done, right? The claim is that using this information will make the derivative not bad. I know, doesn't look promising, right? So I'm starting out with natural log of my thing, right? So natural log of y equals natural log of this behemoth. And then I use my log rules to break everything apart. So that's what this is, right? So I have, again, the powers, the 2 and the 3 are becoming coefficients. The stuff on the top is all positive. The stuff on the bottom is all negative, okay? Now I'm going to try to take a derivative of this mess. Again, still not looking great, but okay, bear with me. I might know what I'm talking about. Apply derivative. All right, so maybe not actually so bad, right? So it turns out taking these derivatives pretty straightforward, right? So I have on the left here, I'm taking the derivative of natural log of y. So derivative of natural log, that's 1 over the thing. But remember, this is, right, derivative with respect to x, and I have natural log of y, so those letters are not the same, so I have this implicit step, right? So this is going to be 1 over y, because it's natural log of y, times y prime. But these pieces, right, they're pretty straightforward. So if I'm going to do derivative of natural log, right, just like we said earlier, I'm going to do the 1 over the content, and then times the derivative of that, but each of these just has, you know, derivative of x plus or minus a number, so each of those chain rules is just 1. And these coefficients are constant, right, so they get pulled out and become the numerator for each one, right? So the 2 becomes this numerator, and I end up with 2 over x plus 1. Here I have 3 over x minus 2, and so on. I need to be a little careful to make sure I remember which ones are positive and negative, right? So these are the parts from the bottom. They should all be negative, which is what happened here. But the derivative step wasn't so bad, right? It wasn't a whole bunch of product rules and a whole bunch of chain rules and a whole bunch of quotient or, you know, follow-up pieces. I didn't have to expand things out. So the derivative step, right? Just the derivative part is done. But whenever I do implicit differentiation, right, I always have that follow-up of having to solve for y prime. So my next step, isolating y prime, I just multiply my y across. And then it's probably a good idea, if I can, to get this to be explicitly defined, because right now it's still implicit because I have that y over here still. But remember, I know what y equals, right? Without the log here, y equaled this behemoth. So I can do that substitution to get just my y prime being explicitly solved for, which gives me this thing. Now, it is worth a moment to think about this because my derivative step was pretty easy, especially compared to the miserable thing it could have been. But the trade-off for that is that my end result is not pretty, right? Like, I still have the behemoth, that didn't go away, and it's not in fully factored form because now I have all of this mess, right? So in some sense, I have sort of lost some nicety to my end result, but I did make the process of getting there much easier. So there's sort of a trade-off between which way you sort of want the misery to come. Do you want it to be miserable taking the derivative, or do you want it to be miserable dealing with it after you've taken the derivative? And really that comes down to what you want to do. If all you need is the derivative, you don't have to do anything with it, then this is great, right? You don't have to deal with it. You can pass it off to somebody else to be miserable. But if you do need to do something specific with it, it might be worth thinking about trying to do it the harder way initially so that you have a better outcome afterward. Regardless, this process, this starting with some natural log, right, introducing natural log on both sides so that you can use that natural log to rip apart a really highly factored piece to make that derivative really much easier to deal with, this is the technique that we wanted to cover. This is called logarithmic differentiation. So not to be confused with differentiating a logarithm, right? Different things. This is the logarithmic process applied to this differentiation, okay? So what did we do? So we've seen sort of a fundamentally new approach, this approach of introducing a log on both sides and using implicit differentiation in order to sort of do something very potentially miserable in a different way. This technique, logarithmic differentiation, is very specifically tailored, right? It's specifically tailored to taking derivatives of things that are sort of in a highly compact factored form. We discussed why sort of, although that is a very specific thing that we might want to do, it turns out to be a very common thing to run into with the way computers happen to work and a multitude of other reasons about how nice factored things are. So it's not so much that it is a rare occurrence, but it is a specific occurrence. So we will have sort of another follow-up video talking about how to recognize when using logarithmic differentiation is sort of an appropriate tool versus when you are just going to make your life much worse. All right, so that is that.